Thank you. Nice to see you back. So let's start again where we were yesterday. And I've been told already by Anna Laura and so on that some of the mathematicians are unhappy with what I've been writing on the board, of course, because of these strange d-dimensional integrals. These things are going to become a little bit more explicit in a moment. Remember, just let me please be patient for another 5 minutes because I wanted to finish what I was discussing yesterday. So remember, we had like integrals of this type, which we called scalar integrals. So possibly many loops. I always put like this denominator here. This comes from Feynman rules. 2 pi to the d is an integration measure. Actually, we will change it very soon because it's more convenient to use another one. But I typically write them like this because this is what you find on QFT, on quantum field theory books, okay? And then we closed the discussion yesterday saying that if I have integrals of the type that we call scalar integrals, so with some, in general, well, sorry, I think I use this notation with only the d's at the denominator. Well, these are the types of integrals, an integral family, as I was discussing it last time, with many denominators raised to possible powers, which could be integers, so, and they could be positive or negative. And then we said that this type of identities are verified. This we called integration by parts identities, because of course, I mean, it looks like kind of an integration by part, but the boundary term of the integration by part is always 0, is assumed to be 0 in some sense. In dimensional regularization is also the only possible solution that makes this procedure that unfortunately I couldn't really discuss, but this kind of standard QFT knowledge consistent, okay? I wanted to make an example. The example might still look a little bit strange because we are manipulating integrals in d dimensions. We don't really know what they are, but this will become clear in a second. So what is the simplest family ever that I can think about? So the simplest family is what we usually call a tadpole at one loop. We need at least one loop to have an integral. And we draw it typically like this. There is no leg that enters into this diagram. And so the expression for the integral associated to this, so if we want, we have a loop momentum k that flows around here, and this particle has a mass, and it tends on itself, if you want. And so following this notation, the integral would be written like this. Again, this is not so important, but then I have 1 divided k squared minus m squared, because this is the propagator or the denominator associated to this line. Now, of course, I mean, if I write this integral like this, it's already kind of strange, right? Because if I write it, you see that there is a minus sign here. We have been discussing and learned that a lot of these examples of the fact that this momenta, this k squared, which is really a dot product, actually lives in what we call Minkowski space. So the metric is, in physics, we write it like this. There is an energy component and then the remaining components here. And this can be both positive and negative, right? So of course, here we have maybe a positive quantity, which is the mass. So there could be a 0 at this denominator. So this is resolved in quantum field theory by what is called the Feynman prescription. So there is a small imaginary part that sometimes is written like this, I0. This is a small imaginary part, or sometimes people write I epsilon. But the epsilon, I don't want to use it because we are going to use epsilon in a second for dimensional regularization. So either we write it an I0, or I could put maybe a delta, where delta is a small positive number, okay? And this practically tells us how the contour is deformed, the integration contour, so that this pole is not a problem. We are going in a second to actually, I will discuss how one can do the so-called Wick rotation, which actually already came up in your, I don't know if mathematicians are aware with this, probably not, but I don't know, but the standard complex analysis is very easy, so that we can practically rotate our integration contour, and this becomes really a standard Euclidean integral in RD, right? And so everything is very simple. So for now, I'm not going to write this all the time, but I'm going to assume that this thing is there, and so this integral is, at least for the point of view of this singularity, is well defined, okay? And so if this is my integral, then the family is very simple, right? The family of integrals is just dk 2 pi to the d, 1 over these denominators to the power n, right, or a1. That's everything I can do. So these are the integrals in this family. And the integration by parts are also very simple. There is only one IBP, one integration by parts that looks like this. I can differentiate, there is only one loop momentum, so I can differentiate with respect to that loop momentum, and I can put the same loop momentum in here to get something scalar. I have nothing else. And then I divide by this guy to an arbitrary power. And this has to be 0. This is my only IBP that I can write. Okay? And now this is a very simple exercise to just take the derivatives, okay? So you see that when I differentiate k mu with respect to k mu, I get actually the number d of dimensions that I'm in. And so if I do the derivatives, let me maybe do it explicitly for once. If you've never seen this, this is how we do this at least. This is my denominator, sorry. Squared minus m squared to the n. This gives me d divided k squared minus m squared to the n, and then minus n k mu, and then 2 times k mu from differentiating the denominator, and then k squared minus m squared to the n plus 1, right? Very simple. So now I can multiply this one times this one, I get the k squared, and the k squared I can rewrite it, as we said already, in terms of the denominators and something else. Right? And so if I do that, I get, you see that I cancel one of the powers of the denominators here. And what I get is the following in one of the two terms, right? And what I get is the following identity. I get d minus 2n in minus 2n m squared in plus 1 equal to 0. I've jumped a few steps, but I hope you can see that, right? I've just really, you see this term d is this one here that gives rise to the standard integral, and then k squared with a factor of 2, it will give a little bit in here and a little bit in here, right? When I rewrite k squared in terms of this one plus the mass, right? And so this is an example of a recursion identity. I mean, in this case, I really can get a full recursion, and the solution is itself, right? There is nothing to do for general powers of n. Which comes from an IBP identity. And so in this case, I can really solve it exactly. This multi-dimensional chess that we were discussing about last time is very easy. There is nothing to do. I just have to do one move or 0 moves. I don't know, depending how you consider this. And that's it. And this gives me all my possible integrals in this family in terms of a minimal number of integrals, which is what? Is going to be 1, because you see, I can reduce every power of n, which is bigger than 0. I can actually reduce it to, if you want, up to n equal 1 here, right? So I can go down, 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 and n equals 0, of course, is a problem, right? I cannot do that. And so this is an example of a reduction. And in the, for example, I can say that, I don't know, I2, which is the squared one, is d minus 2 divided to m squared I1, right? And this tells me that I3 can be written in terms of I2, and so in terms of I1, and so on and so forth. And so in this case, the family, the tadpole family, the tadpole family has one master integral. That's what we say. Of course, I can choose the master integral in different ways. If I follow this standard reduction, and this is what people have been doing for let's say 30, 40 years, before like the developments maybe of the last 15 years, I would always choose, I would tend to choose the integral with the lowest power right here as the master integral. So the master integral could be I1, right? So this is my basis, that this dimensional space is one-dimensional, and every integral in this family can be expressed as some rational function times I1, right? So in this sense, I1 is my master integral. I invite you, if you want, I mean, there will be an exercise session. You don't have to do it if you don't want to, but you can try to do the same exercise for a slightly more complicated example, which is a bubble. If you have never done it, this could be useful. So this integral looks like this. And so, of course, the full family will have, say, A and B here as different powers. And so I will consider integrals I, A, and B. And now there are two integration by parts identities because I can, of course, I can differentiate with respect to K. And inside here, I can put either K or P, right? There are two momenta. There is the internal loop momentum, but there is also the external P. And writing down these two IBPs and also noticing that there is also symmetry. So, of course, this is equal to this. I can see just doing a shift if I send K to K minus P, which you see are all operations that I assume I can do because the integrals are well defined and convergent and whatever. This shows that these two integrals, these two things are the same. Then I can put in all these things together, I can prove, for example, that I12 can be written like this. I hope I've not messed up any signs. I10. You see, this identity is a little bit more complicated now. I've not derived it for you, right? You need two IBPs derived for special values of A and B. In particular, if you start with A and B equal 1, both of them, and you derive the two IBPs, you can solve them. And you can also use, I think in general, you also need to use this one, because this integral here, you see 1, 0. This is actually the tadpole, right? It has one of the two propagators is missing. This propagator here is missing. So it's the integral that we have already encountered before. And we already know its own reduction identity if it appears with higher powers. So you see that in a case like this, as soon as we go to a family which has more than one propagator, then we are going to find in general more than one master integral. The first master is the tadpole that we already encountered. And the second one is the bubble, right? This already corresponds to what I was saying yesterday. I mean, I start from the bubble. Here I can pinch, I can remove one of the two propagators. And so inside here, I will necessarily also have the tadpole. This would be the family tree, right? And this is the bubble. And this here is the tadpole, right? Does this make any sense? Yeah? I hope this is simple enough. I realize that in order to do this, the only problem is that you have to accept that these integrals are well defined and you can manipulate them. But if you accept that you can manipulate them, you just manipulate them, and this is like, I don't know, calculus 1, right? There is nothing, you just have to be able to take derivatives, right? Or maybe calculus 2. Of course, now we want to understand maybe a little bit better what these integrals look like. How do we compute them? Because these IBP identities, they allow us, if we can really convince ourselves that they are well defined and we can do them and so on and so forth, they allow us to reduce complicated integrals in terms of possibly simpler one, whatever that means, or at least a basis of integrals with coefficients that are just rational functions in the dimensions and in the kinematics, so in the p squared, in the SIJs that Bernd was talking about before, and the masses, right? But we would like to compute these things. So today's lecture is going to be about the first way of computing these things, which is direct integration, okay? And in particular, we will derive, for those of you that have never seen it, parametric representations for these integrals, which also allow us to make a little bit more sense, at least for a mathematician, I would say, of what does it mean to integrate in d dimensions, okay? So, any questions, or can I? This was probably almost too easy. But you never know, right? Because the easy things are difficult and difficult things are easy, apparently. I think it's very loud. Okay. So, of course, this is an integral. So if it's really an integral, the first thing I can try to do to solve the integral is to integrate, right? So to see if I can do the integral. That's what direct integration means. Of course, the reason why it's called direct integration is because typically we don't solve the integrals by direct integration, by indirect integration. We do other things, okay? But direct integration is very powerful, nevertheless. There are a lot of interesting results. So let's start with the tadpole, okay? So that this becomes very explicit. So this is the only integral that we can really solve. Well, maybe not the only one, it's a too strong statement, but it's definitely the only one that we can easily solve by integrating over k, also trying to make sense explicitly of what does it mean to do this integral in d dimensions. So first of all, I told you here there is a little imaginary part, right? So the first thing that we do is what is called a Wick rotation, which just means that we want to rotate, if you want, from this Minkowski kinematics to really RD. Okay, so we want to really do the integral in Euclidean RD. What does it mean? Well, in practice, I mean, it's actually very easy. So this denominator here is k0 squared minus, I write it with a vector. This is the vector part, minus m squared plus I delta. And I'm practically doing an integral, really, you were asking explicitly, where am I doing the integral? And I'm really integrating with this k0 that goes from minus infinity to plus infinity. And then I'm integrating over all the d minus 1 remaining components of k, okay? Now, if I have something like that, of course, if I look at the complex plane in k0, where I have the real part of k0 and the imaginary part of k0, and I look at this denominator, I see that there are two poles, right, in k0, which correspond, if you want, to k0 equal to k squared plus m squared minus I delta and plus I delta, right, because I have to take a square root. And so the two poles, actually, one is here and one is here, okay, if you do it properly. You see that there is one pole here, which is square root of k squared plus m squared plus I delta, and the other one, right, on the other side. And so what I can do, they are a little bit raised, right, due to this I delta. And so I have to integrate here. So instead of integrating here, I just do a rotation of the integration contour using Cauchy theorem. There are no poles here, so this is 0. I send these contours to infinity, and I practically can see that, now I'm writing it in the opposite direction. Let's try to write it in a consistent direction at least. Right? If I go around this contour, then I get 0, and so through this 0 contour, I can trade the integral from minus infinity to plus infinity to the integral along the imaginary axis, right? And when I do this, then this variable practically, I can do a change of variable, and this becomes ik, right? Because I integrate along this, and so this one becomes also a minus. I'm doing it a bit fast, but it's really like simple. So through this Wick rotation, the integral is actually equal to an I overall, and then an integration, which now is really on RD, okay, of 1 over k squared plus m squared. Now this is really integrated over RD. Yeah? The integration contour before, in k0 only, was just the real axis, from minus infinity to plus infinity. And also in the other case, I would go from minus infinity to plus infinity. I would integrate everywhere. Now, well, what I'm doing is that I'm rotating it like this. So now I'm integrating from, if you want, to plus I infinity to minus I infinity. And then I'm renaming the variable I k0, in a sense, k Euclidean, right? Or k4, I don't know. So I'm just integrating along this one. So the I comes out. And this becomes now positive definite. Well, sorry, relevant, you said? No, it's just because now I can just write it like that, and then maybe you're happy that there is no singularity. So when we manipulate these integrals, we always imagine that these denominators, there is at least a kinematical choice. If you want, there is this Wick rotation that I can do, where these denominators here are positive definite. Right? Okay, it's not true here. But I'm going to do some things that assume that. Okay, in a second. That's why I wanted to stress this. I mean, this is, I think, very standard stuff that you learn in QFT1, typically if you're a physicist, but if you have not taken physics, I don't know, QFT1, then I don't know if you've seen this or not. But does this make sense for the people that have never seen it? It's just a way to say, I can rotate the integration contour, and so I really care about Euclidean integrals, because also Anna Laura was asking me, where is this integration going, right? And it's really RD. You can really think about it as RD, okay? You're not convinced, but you're a physicist, so you should.
I have to be honest.
Yeah. Mm-hmm. Yeah, but that's why you then redefine it, right? So practically, you first rotate the contour, and then it goes from minus or to plus infinity to minus I infinity. And then you redefine it so that the new k goes in the real ones. Is this k4? So if you want my k, you know, my k0 goes from here to here, which means that k4 goes from on the real values, right? Because it's I times infinity, right? Yeah. So the I practically just gets carried out here, and this is completely Euclidean after that, right? There is also a minus sign that comes on the denominator. It would be a minus I, but then there is also a minus sign that comes on the denominator if you do it properly, because it depends if you can plus I infinity, minus I infinity. If you do it slowly, right, then but it's really just a Cauchy integral. Okay, and then once I have something like that, then, well, the first thing I'm going to do is that I'm going to change the integration measure, because this actually gives very ugly results. So I'm going to consider a slightly different integral, which is ddk, and I'm going to assume that actually the integral I started from, this is what we always do, is actually this one. So with an I at the denominator and a pi to the d half. Why the I at the denominator? Because the I at the denominator, when I go to the Wick rotation, just cancels. So it's actually very nice. And the pi to the d half you will see in a second. Why? Because it actually gives also nice results. And then on top of this, I'm also going to multiply this by e to the epsilon gamma e, where gamma e is the Euler-Mascheroni constant. Mascheroni. And epsilon is 4 minus d divided by 2. This is a little bit of a technicality, because it makes me get very clean results when I look at how this integral looks like close to 4 dimensions, which is the number of dimensions that I'm interested in. Okay, so that's why I define this epsilon, which is 4 minus d divided by 2. So epsilon is equal to 0 in 4 dimensions. And here I get the Euler-Mascheroni constant. You will see why. And so on. Well, I mean, you probably already see why, because from this point of view, this integral is so simple. You see that immediately there is no dependence on the angles, right? So the angles can be integrated out, and the rest gives you practically a beta function, okay? Now, since the angles can be integrated out, you see that I can very easily, I could imagine, okay, to say this integral, I do it for a number of dimensions d where the integral is convergent, right? It could be d equal 1, or I don't know, d equals 0, possibly even, okay? But what we actually do is that we are just going to imagine, as I said, that we do an analytic continuation, right, in this. So what we have like is the angle, right, here, and then an integral from 0 to infinity. Let me put the pi d over 2 here, and then dk kd minus 1 over k squared plus m squared, right? This is our integral. Now that I've gone to polar coordinates, the angle has come out completely. Very nice. And the angle is just 2 pi d over 2 divided the gamma function d over 2. And this is the only analytic continuation that I really have to do, right? I know actually very well how to continue, if you want, the angle here from integer values, if you want, of d to arbitrary complex values. This is the analytic continuation, right? I have to practically know how to analytically continue the factorial. Everything else, once I've put it in this form, is actually just powers, right? So, and everybody knows how to analytically continue powers. I can do k to the power d, which can be a complex number, right? So what I'm doing is that I'm really taking the integral. I'm assuming that I can write down this expression for some values of d, okay? And then I analytically continue it to d, which becomes complex. And I can do that because the only thing I need to know is the gamma function and the power function, right? And this I know how to continue. And so now this integral here is also very easy because, well, maybe I can write it out explicitly again. This is dk kd minus 1 k squared plus 1 plus m squared, sorry. Now this integral here from 0 to infinity, if you do a few easy change of variables, you see that it's a beta function, right? Yeah, I can write it on the other board. And this becomes e to the epsilon gamma e. Then I get I d over 2. I'm pulling out the mass here to the d minus 2 over 2. There is my 2 pi d half gamma d over 2. And then I have an integral from 0 to infinity in dt t to the d minus 1 t squared plus 1. Right? The first thing that I've done is that I've rescaled k by m, so that I pull out this power of the mass, and then I get a 1 here. And then I can redefine t squared equal u, right? And then I get, finally, e to the epsilon gamma e, m squared d minus 2 over 2, 1 over gamma d over 2, and then integral from 0 to infinity du u d half minus 1. 1 plus u. Yeah. Well, I went to polar coordinates. So this is the modulus of the vector squared, right? I went to spherical coordinates in d dimensions, and then I continued them to d complex. Exactly, but also here it's just a length, right? It's always just a length, because the good thing, or the easy thing of this integral is that it does not depend on any angles. Right? In general, integrals will depend on angles, and so we will have to do something more, right? Just wanted to show this explicitly, because here you see really what does it mean to do this integral in d dimensions. That's what it means, okay? Does this make sense, or is it strange? Omega d is the angle, right? The d-dimensional angle, which should be, if I remember correctly, this, right? When you continue it through the gamma function, right, you can continue the factorial to the gamma function, and you get this formula, right? So what I was saying is that really this continuation to complex D really means only being able to do an analytic continuation of a power function and of the gamma function, well, of the factorial, right, which becomes the gamma function, yeah? Which one, sorry? Which line? This one? So here I just changed the integration measure. I just decided to change it, right, myself. So somehow the I wanted to get rid of it because it always appears through this Wick rotation, so I put an I in my original. Instead of having 2 pi to the d, I said, okay, let's call this I pi d half. I mean, it will change the integral a little bit, but I mean, I will have to correct for that when I do physics. But as long as I do math, I don't care, right? Because it's just a trivial correction. So the I has gone away. And then I've remultiplied on purpose by this thing, because you see that from here, I get a lot of gamma functions. I will get a lot of gamma functions. The gamma functions, when I expand them close to epsilon equals 0, which is d equal 4, will produce Euler-Mascheroni constants, which I don't like. So I want to actually absorb them out in a prefactor that somehow goes away, and this prefactor, when everything is finite at the end and I can put epsilon equals 0, the prefactor gives me 1 and disappears, right? This prefactor for epsilon equals 0 and d equals 4 is 1. And so I really don't care about it at the end, okay? That was the logic. Sorry if this was a bit fast. On one hand, I don't want to bore you. On the other one, I don't want to, I don't know. I have the feeling I will always either confuse or bore someone. But okay, now you recognize your beta function. Do you recognize the beta function? Yes? Physicists do, maybe mathematicians, depending on what, I don't know. So the beta function, beta, alpha beta, is integral from 0 to infinity du u alpha minus 1, 1 plus u alpha plus beta. And this can also be written as gamma of alpha, gamma of beta, gamma of alpha plus beta. The beta function, right? So you recognize it here. So you put everything together, you see you get nicely the gamma function that cancels this one down here. And so at the end, the result is e to the epsilon gamma e, m squared e minus 2 over 2, and then gamma 1 minus t over 2. That's what you're left with. A lot of the crap cancels, right? And I'm just left with this gamma here that is practically coming from this numerator here. Okay? So this is also, you see why nicely also the pi that I had at the denominator went away. So I cooked up my integration measure somehow so that things are as nice as possible. And now you see that I can define, as I said, I can use this epsilon, which was 4 minus t over 2, right? And I can expand close to epsilon equals 0, right? And if I expand close to epsilon equals 0, what do I get? I get m squared to the minus epsilon, which is apart from here. Then I have another m squared that is left from here. And then if I expand the rest, I get minus 1 over epsilon, minus 1 plus pi squared over 12 epsilon plus higher orders. This is big O, yeah? So you see that I get a 1 over epsilon. This is a pole, right? This is a pole 1 over t minus 4, which tells me that the original integral was divergent in 4 dimensions, right? I actually expect to see a divergence somewhere, but now I've regulated in this way. This is why it's called dimensional regularization. And when I expand close to the number of physical dimensions, I get poles. So these functions are always just meromorphic functions in the dimensional regularization parameters, okay? Like the gamma function, they only have poles there. I can, of course, expand to higher orders. And you see that thanks to this factor that I've put here, I don't get any Euler gammas or any strange things in here. Otherwise, I would have a lot of Euler gammas and other ugly factors popping up in here. This is a zeta 2, right? Practically divided by 2 and so on. So there are like the standard numbers that you get. Okay, so this is what it means for us to do these integrals, okay? So this is an example. It's actually the simplest one that we can do. But now what about an integral that is not so easy, but instead depends on angles, right? Because in general, when I wrote the bubble before, imagine you want to compute this integral here. This integral here also depends on the scalar product between k and p. So it depends on an angular integration. And the more of these external momenta I have, and the more loop momenta I have, the more angles I have, and these integrals become impossible. Okay, they become very difficult. So the first trick that we are going to do is derive a parametric representation where we practically put our integral somehow in a sort of an hypercube, okay, where we integrate over scalar integrals, sorry, over scalar variables, which are called Feynman or Schwinger parameters, and then we don't see angles anymore, okay? Angles don't appear. So this is what I'm trying to do now.
Lorenzo?
Yeah?
May I make a comment?
Even 2?
Formula is a function of t, but from conversations that maybe mathematicians.
Go ahead, yes.
Yeah, my comment is that when and we parameterize them and we get this formula. But then here we have to use that same formula also for non-integration. So if you wish, you could view this formula as
a definition. Yeah, I mean, it's the analytic continuation, right? I think.
It's our choice of analytic continuation or definition.
I think mathematicians are not worried.
Yeah, I think if you think about it, I mean, if you think about it.
We don't know the calculus.
No, but I said but I think my understanding, but I mean, you should tell me if this is not true, but my understanding is that if you think about it really as a procedure of analytic continuation, then this is a well-defined, unique analytic continuation indeed that you can do. There is no other choice, okay? So that's it, I think.
I don't think anybody's worried about not being
Is it better now? No. Yeah. I mean, it can also happen exactly like the Riemann zeta function, right? It can happen that, for example, this integral that we started from, if you look at it, if I wrote it in 3 dimensions, it would be divergent. In 3 dimensions because I have too many powers of k at the numerator, right? But if you compute now this and you put d equals 3, you get actually a negative finite result, right? The Riemann zeta value that of 1 is minus 1 over 12 or something like that, right? So it's exactly the same. So of course, the integral, somehow the integral makes sense as a representation only when the integral converges. If it doesn't converge, I have to think about it as the analytic continuation of that, right? This is the only... I found it typically effective with mathematicians to explain it like this, but also to students, because also students of QFT, which come from having had a lot of classes given by mathematicians, when they finally teach QFT, they really hate us because of all these things, because we cannot be that precise anymore. And but okay. Usually first year of master, so fourth year, right? You need to have done quantum mechanics and special relativity and all these things, right? Because quantum field theory is the mixture of quantum mechanics and special relativity. So it typically comes in your master. Okay. Now I have to go a bit fast, sorry. But again, we are doing simple manipulations, okay? So first thing, I'm assuming that all my denominators, so we are talking about integrals, right, which have a lot of denominators. We wrote them already like this, okay? I'm going to maybe update my integration measure so that it respects what I did before for the one loop case. So I'm going to consider these integrals. See that I've changed the integration measure a bit. 1 over d1 to a1, dn to an. And I'm going to assume that I've done some sort of a Wick rotation, or I can do it at some point so that all these di's are positive. Okay? Positive definite. I mean, actually, it's important that the real part is positive, okay, for what I'm going to do. Because what I want to do is that I want to use the following formula. D to the alpha is equal 1 over gamma alpha integral from 0 to infinity dx x alpha minus 1 a minus x d, okay? And so I'm assuming also that the real part of alpha is positive. You can generalize this if they are not positive but negative, but let's go with a simple one, okay? Real part of alpha is positive, and also if you want the real part of d. Right, so that this formula makes sense. And I'm going to actually use this formula. So these parameters are what are called Feynman-Schwinger parameters to rewrite all my propagators in here through that formula, okay? So this formula is going to become, it's going to give me then e to the L epsilon gamma e. This is a prefactor. Then I have a product, I from 1 to n, integral over all these parameters, one for every propagator, so I call them xi's, xi to the alpha I minus 1, ai minus 1, divided gamma ai, and then I have an integral of p product over all the loop integrations, and I get a big exponential of x1 d1 plus xn dn, right? This is just if I use that formula in my integral. And now, I mean, what do I recognize that this quantity here, this, let me call it q, right? This q is a quadratic form in the loop momenta, right? So in particular, you can, if you think about it 2 minutes, you can see that you can write it like this. Sum over ij from 1 to L of ki mij kj plus 2 sum I that goes from 1 to L ki vi plus j, where, what is this? So this is a matrix L times L of scalar entries. It multiplies all the possible loop momenta, right? I really take them as 2 different loop momenta in there. And these are L d-dimensional I'm going to do an example, vectors. Okay, and this is again a scalar. Okay, so think about it at what happens. I mean, every propagator is written as something like some loop momenta summed with some external momenta to the power 2 quadratic plus a mass or minus a mass, okay? So when you expand everything out, you're going to get either products of loop momenta or loop momenta times something else that is not a loop momentum, or something without any loop momentum. In this sense, this is a quadratic form in the loop momenta. What I do here, I'm going to do an example in a second, so it will become maybe more clear, but I want to just say what it is, because if you sit down and you try to do it yourself, it's actually very easy. I practically put the quadratic form in canonical form, practically completing the square, right, in the case. And once I do that, then once I've completed the square, then the integral in K becomes trivial, okay, because it becomes a Gaussian integral. So I do practically my integral, and I do the integral in K, in all the loop momenta. And what I get out of this is the following. An e to the L epsilon gamma e, integral from 0 to infinity, all these parameters, I from 1 to n, dxi xi to the ai minus 1, divided gamma ai. And then I get a polynomial here, u, to the power minus t over 2, and an exponential of minus f of xi divided u of xi, okay, where u of xi is the determinant of the matrix M that I wrote here. Maybe let me just call it M without indices, otherwise, right, of that matrix M. And F is U times J plus V transpose M minus 1 inverse V. Okay, so this is a product. This is a vector times a matrix inverse times a vector again. Okay? So it actually really comes from, it's a Gaussian integral. It's a general Gaussian integral, and you just do the Gaussian integral. Okay, that's what you're doing in this loop momenta. And out of these Gaussian integrals that you do, you get two polynomials, a U polynomial and an F polynomial. The F polynomial is built also out of the U polynomial and the determinant and so on of this matrix. And these are what are called the Symanzik polynomials. Yeah, sorry, I want to.
So one thing that I don't understand is, so I have these D's, the algebraic geometry, very interesting. And they look very different. They're very, very different. They represent the same integral.
Yeah. I think this is a. Yeah, this is a wonderful question. I mean, it's the reason why typically, in order to see the geometry associated to the integrals, we always to the integral. Yeah, but even to the. So now I don't know exactly what you. But even so, somehow to study the integrands, we always go to a parametric representation because it's typically simpler. But there are different ones. This is not the only one. There is another parametric representation which I'm going to discuss if I manage. I don't know, which is called the Baikov representation, which is actually completely different than this one and looks completely alternative. But of course, if you study the geometry associated to those polynomials that you get in that case, it has to be the same again, right? Than in this case. You might also get a different number of variables, right? Different number of parameters in the two representations. So maybe this is more a question for you. I don't know if someone has, I don't know. The answer to my... I think this is for me. Yeah, very fundamental question. Yeah. I'm trading, I mean, in a sense, what I'm doing in practice is that I'm trading all the angular integrations, which I can get rid of through this Gaussian integral, through these integrations over these parameters. That's what I'm doing. But now, I mean, it is possible, it's not impossible, right? I mean, you can find different, nothing is impossible, as Johannes would like to say, I think. But you can find like different parametrizations, right, that can be more, where the geometry associated to these varieties is actually more or less manifest. And sometimes it's easier or less easy to see, right? It is, I don't know. So I think this is a question, it's a very interesting question. I don't have much more to say about this.
In particular, maybe you could ask it, how do you
I'm just writing something, but yeah. If there was a canonical representation for these integrals in this sense, that would be also interesting to know, right? There is one that is, we also, sometimes we do, so this representation that I'm doing, that I'm discussing now, this Schwinger Feynman representation, is completely insensitive in a sense to the number of dimensions I'm interested in at the very end, right? Because you see, now I've turned everything into, again, something where the analytic continuation to D complex is trivial. I just need to be able to continue possible gamma functions if they come out of all this process and powers, right? No. The number of master integrals can change if you change D. For generic D, then it's fixed. Then it's fixed. But if I fix D equals, say, to number 4 or 2 or whatever, then it can degenerate. Yeah. It is the Euler character. It's the Euler characteristic. Yeah. Well, you definitely see it here. You definitely see it here. There, I don't know. Yeah, you definitely see it here. Actually, there is another representation that is called Lie-Pomeransky, where there is only one polynomial, and it's typically used to study the Euler characteristic associated to the problem, right? That's kind of more convenient, again, for that particular, to answer that particular question. Okay, I just wanted to say, I'm going a bit fast on this thing, but these two polynomials, one can prove in general that they are homogeneous polynomials in these parameters, x. The first one is homogeneous of degree L, and the second one is homogeneous of degree L plus 1, okay? And let's make maybe an example. If I take the bubble, which is the example that we already played with a little bit, and then this would be my first propagator, and this would be my second propagator, k plus p, as we already said many times, p. Then this q, this form, then becomes x1 k squared minus m squared minus x2 k plus p squared minus m squared. So it's really, see, the sum of the parameters times the two propagators. There is just two of them. And so if I open it up explicitly, I can write it as minus k times x1 plus x2 k minus 2 k dot p x2, and then plus x1 m squared plus x2 m squared minus x2 p squared, right? Opening up all the sums. And now you see that this is my matrix M, which is not really a matrix. In this case, it's a scalar. It's a 1 times 1 matrix, okay? In this case, there is only one loop momentum. As we said, it has to be an L times L matrix. So it's a 1 times 1 matrix in this case. This one is what I called, I think, V, the vector V here. There is, of course, only one, and it would be P times X2, right, in this case. And then finally, this would be J, right? And so, of course, now if you compute it, you see that the U polynomial becomes x1 plus x2. And the f polynomial becomes x1 plus x2, x1 m squared plus x2 m squared minus p squared plus p squared x2 squared 1 over x1 plus x2, if I just write out all the terms as they are. And now I simplify things a little bit, and then what I get is m squared x1 plus x2 squared minus p squared x1, x2. Okay? Now you see that this polynomial is homogeneous of degree 1, this polynomial is homogeneous of degree 2, right? There is a square here, and so on. Now these things can be proven actually very rigorously, all these properties and so on. I just don't have time to do all these things in detail. Good, so this is what is called Schwinger representation. Now let me go to Feynman. So Feynman representation is particularly nice because we are going to practically get a representation which I think mathematicians call a projective integral, which uses, if you want, the homogeneity of these polynomials. And so it also allows us to reparameterize the integration domain in a very general way. So we want from Schwinger to Feynman. Not sure that Feynman knew that this integral was a projective integral or what that means, but somehow. So the idea is the following, is that you use the fact that these parameters that we introduced, they're all positive, they're integrated from 0 to infinity. So the sum of all these parameters is positive, okay? And so what I can do is that I can insert in Schwinger, so in the representation above, the following identity. Maybe there is a more elegant way to do it, but I just take the first line here on the left and I insert this one, which is satisfied because the sum of the parameters is always positive, right? So this integral is equal to 1. And then I do the integrals, okay? I do some renaming of variables. It's done in details here. I can share the notes if you want, but this is actually very well known. So, I mean, I don't know. I don't have a lot of time, so when it's not really only algebra somehow or analysis, maybe it's not algebra. And what I get out of this integration, the following. Gamma, let me call this alpha minus dl over 2 divided by product j that goes from 1 to n of all the gamma ai's, aj's, not ai's. And then an integral from 0 to infinity of a product j from 1 to n d uj. I've also renamed the integration variables from x to u because I did some rescaling in between. And then alpha, I hope you can see these are powers over 2, and this alpha, did I define it? Alpha should be the sum of the a's, okay, which are the powers. Write it somewhere? Apparently I didn't. So you see what has happened practically through this trick. I insert this delta function, and then I do some remanipulations, and then I can do, through this delta function, I can actually do the integral over the exponential completely. And that actually gives me some gamma functions in front, and I'm left only with the polynomials, okay? If you want, we could do it if you want directly, more explicitly if you want in the exercise session, but it's kind of standard and it's done explicitly here. But now you see that actually in this representation, now that we have written things in this way, this U, as I said, I changed their name a little bit because they came from a rescaling of the original X Schwinger parameters, but in the end, they're integrated from 0 to infinity, and there is this delta constraint. Now, this is how we learn this, as I said, somehow in school, right? So when we learn Feynman parameter representation in QFT, this is what they give us. They give us something of this sort. So we have this delta function of 1 minus the sum of all the Feynman parameters, and then there are these two polynomials, which are exactly the two polynomials that we wrote before. And what is that? Since the polynomials, by the way, since the polynomials are homogeneous, I hope it's clear, I have practically, these U's are nothing but the rescaling of the original X's, but everything comes out, right? Because the polynomials are homogeneous. So these are exactly the same polynomials as before, just written in terms of the variables U instead of the variable X, right? Because I can rescale anything out using the fact that they are homogeneous polynomials. It's not important in a sense, but if you want, I can tell you, I have to do two changes of variables. So I think the relation is, let me actually write it explicitly here. I think I insert the delta function and then I just rescale xi to t ui through that t that appears in the delta function here, so that it comes out, this t. And then I have to do another change of variable from t to t prime u divided by f, the ratio of the two polynomials. And through these two changes of variables, then I can do the integral over the exponential, and then it goes away, and that's what I'm left with, okay? So it's written explicitly. If you want, I can share these notes, yeah.
So to the case where some of the use is
exactly.
just integral.
Exactly.
What happens to the
Exactly. Yeah.
the
Well, the point is exactly this, right? So it's the fact that we have now actually, so we have practically made the integral explicitly homogeneous, if you want, in everything. And I can reparameterize, if I understand your question, I can actually reparameterize the simplex, that is the one that you're discussing about, as I want, right? So the point is that what comes out of this representation, which is the reason why this is particularly nice, is that this is a projective integral. You see from the degree of the polynomials there, that if you do any reparameterization of these U's, any rescaling of the U's, everything cancels out, and it becomes, it's a homogeneous of degree 0, if you want, the integrand, which also tells me that what I was saying, this thing, that is how we learn it, kind of in school, so we are, I say it in school, but in actually the fourth year of our university, what we are supposed to do is take in one of the parameters and express it as 1 minus the sum of the other ones. Is not the only possible parameterization of this simplex, right? So I can do other possible parameterizations and do it as I want, right? But if you want, it comes from the fact that there was some hidden stuff still in this representation here. Or so that representation there was not, if you want, was not explicitly, or maybe I should use the word manifest, since you say that this is what manifestly projective, right, from that point of view. So this is a projective integral, that's what I'm trying to say. So one of the directions you can always get rid of, right? The integral is projective, so it's in n dimension, but it's truly in n minus 1 because of its projectivity. But this projectivity, I don't know if that's the right way to say it, was hidden there, and now it's manifest, okay? I don't know if that answers your question. Yeah. Good. So as I was saying, so when we learn this, typically people tell us, our professors, whatever, told us to just use this delta function and remove one parameters in terms of the others. But of course, as you were saying, I mean, the point is that this integral is a projective integral, so we can reparameterize the simplex as we want. And this simple fact is in the physics literature is known as Cheng-Bu theorem. I don't even know if it has a name in math, or it is completely obvious that this is a fact. This is how people call it in the physics literature. So if you hear about Chang-Wu theorem, that's what they mean. So they mean that you can reparameterize this as you want. In particular, you can put maybe only one of the parameters equal to 1 and integrate the others from 0 to infinity, or a subset of them, or whatever, right, you want to do. Good. Now, how much time do I have? Is it over?
15 minutes.
I still have 15 minutes, okay.
Actually more like 13.
13, yeah. No, so now, I mean, of course, do you have any questions about this? So I went a little bit fast, but if I really want to prove all of this, then it takes me like half an hour just to write all these formulas on the board, but there is really nothing too complicated going on except changes of variables, and then trying to realizing that actually this representation has this very important property of being projective, right? And so this is important because it becomes indeed manifest only in this case. I can maybe write then explicitly what happens for our friend the bubble, so that we also see what a less trivial integral looks like. And let me also add, so typically when we talk to mathematicians, indeed, now I'm thinking about Francis Brown, that was one of the first people that got interested in Feynman integrals from a mathematical point of view. This representation is the one that they love, right? Because, of course, there is no strange integration over d-dimensional loop momenta with d complex, I don't know what. It's just an integral over a simplex of some polynomials, right, raised to some powers. So typically, I think what you can do is that you can take this as a definition of your Feynman integral. So if you don't like the other representation, you can say, for every Feynman integral, this is what defines the integral that I have to compute. The other representation doesn't exist, okay? That's a possible, I think this is what Francis likes to do, but I don't want to speak for him, but I think this is my understanding. He really doesn't like the loop momentum representation. Sorry? Okay, the names, okay. I don't want to enter into this, but this is, I mean, Feynman called them UNF, and so we are, since he was the first one, I think that we have to respect that. I think he called them UNF, but I'm not sure. Okay, good. So what happens for the bubble? For the bubble, we get then the integration measure, then this gamma from the formula that I wrote there. Then there is the integral over this simplex. If you want, I can write it like this, and then I don't need to write the delta function every time. And then I have the u polynomial, which is now raised to 2 minus d, and divided m squared u1 plus u2 squared minus p squared u1 u2 to the 4 minus d over 2. This is what the bubble would look like in this representation. And with this delta, I'm meaning now this simplex, right, that we just described before, which is now I can reparameterize it as I want. Now you see that, if you want, maybe let me write it. Giving too many things for granted. So now, the important thing here is that you see that, well, I don't know if it's important, but at one loop, one can actually see that the u polynomial at one loop is always the sum, always ends up being the sum of all the Feynman or the Feynman parameters. This is always true at one loop, is not true at higher loops, which is also the reason why, of course, Feynman, that was, as far as I know, the first one to use this trick, but also Schwinger and so on, Feynman and Schwinger, they were actually afterwards always choosing the solution where you put the sum of all the Feynman parameters equal to 1. Because you see from here, it's clearly a good choice, right? This one is going to disappear. This one disappears completely because it becomes a 1 to some power. And so the integral becomes as simple as possible. This is true at one loop, but at higher loops is not typically true. At higher loops, there can be other choices to parameterize the simplex, which are actually more convenient. So in this case, I'm going to say that u2 is 1 minus u1 and is 1 minus u, so I just call it u. Okay, and so my integral becomes m squared to the minus epsilon e to the epsilon gamma epsilon gamma of epsilon. I've also reintroduced the epsilon as before, and then an integral from 0 to 1 du 1 over 1 minus p squared over m squared u 1 minus u to the epsilon. You see what I've done here? I've used the fact that these are also, on top of the fact that, of course, the u and the f polynomials are homogeneous polynomials of degree L and L plus 1 in the Feynman parameters, the polynomials also have to be homogeneous in the kinematic invariance and the masses. And this is just because, from the physics point of view, dimensional analysis has to work. The final integral has to have the right dimensions. So everything has to scale out with the right dimension of the energy. Okay, there cannot be here an m to the 4 and here p squared if p and m have the same dimension. Okay, so what I'm doing here is that I can always use this fact and I can always pull out one of the parameters, if you want, that defines the mass dimension of the integral. This is also what we typically talk about, like the mass dimension of the integral, which is m squared to the minus epsilon. Remember, epsilon is 4 minus d over 2. Okay? And the rest, the remaining integral here, is what physicists typically like. This is a dimensionless integral. So if you hear about this, for mathematicians, this doesn't mean anything. What it means for us, it means that the only dependence on the physically relevant variables, which are p squared and m squared, appears in ratios where there is no dimension. So the dimension, the energy dimension cancels out. P has the same dimension of a mass as the dimension of an energy. P squared of m squared is a variable that is dimensionless. So I can write, for example, a logarithm of p squared over m squared without having to ask myself, what is the dimension of this object? If I had something like this in my result, then I would be very unhappy because I would have to ask myself, what is the dimension of log of p squared if p squared has dimension energy squared? And this is what physicists really don't like. So this is something that also mathematicians don't appreciate, I think. I don't know if you ever encountered this type of discussions. But dimensional analysis is very useful because it tells you immediately what the result can or cannot depend on, just using this. You know that it has to depend on ratios, right? It cannot depend on the two variables independently, right? This is how we think about this. Okay. Now, very good. This integral is very simple. We can do it. Let's do the integral. And so we get m squared to the minus epsilon. And then I'm going to expand now in epsilon. So I get the 1 over epsilon again, then a factor of 2. And then, before the factor of 2, I wanted to write minus integral from 0 to 1 du logarithm of 1 minus u p squared over m squared plus higher orders in epsilon. Okay, so you see I have expanded this integral in epsilon. At the first order, the integral from 0 to 1 just gives me 1, and so I get my pole from the gamma function in epsilon. This is again a divergence, what we call a UV divergence, but it's there, and whatever. And then I have an integral over a logarithm of something. Now you see also here I have to pay a lot of attention to where my variables are, right? You see that if p squared over m squared is positive, if actually, in particular, if p squared is bigger, you can check that if p squared is bigger than 4m squared, then this thing can become negative when u goes from 0 to 1. And so this logarithm can produce an imaginary part, and this is what we were calling a branch cut before. So if you remember, at the beginning of our lecture, I talked about branch cuts, and here I can actually show you this branch cut, right, popping up. If you try to solve this equation, this is a quadratic equation, you get some square roots, and you see that the equation can only have solutions, and it can change sign, in particular when p squared is bigger than 4m squared. What it is p squared bigger than 4m squared, where we have our bubble, this is p squared, and these are the two masses. So when p squared is bigger than 4m squared, I have enough energy to produce these two particles on shell. And this is what I was saying before. And so this is my branch cut, my discontinuity that can only appear. I already knew this, that this had to happen, right? I already knew that my result had to know about this before doing the calculation. And this is how it knows about it, right? Through this logarithm. Is it kind of clear? Because at some point I talked about branch cut, you said that this is something very strange for mathematicians, right? Really thinking about the results. Feynman integrals and Feynman amplitudes are practically analytic functions in the complex plane, analytic functions of the kinematics, modulo poles, and branch cuts. This is what people typically say, right? So there are poles, which are these poles that we discussed last time when I have a single particle going on shell, and there can be these branch cuts, so discontinuities, logarithmic discontinuities, or square root discontinuities in the complex plane, right? In this case, in the variable p squared over m squared, which is the only variable on which the result really depends on. So if you want when p squared over m squared is bigger than 4, then there is a branch cut, right? There will be 4 here, and there will be a branch cut. That's what we mean, right? In the plane, in the imaginary, in the complex plane where this function exists, okay? It's also actually very convenient here, and then I think I stop. I was hoping to say something about Baikov, but whatever, maybe we have to live without it. Is for today. So I'm going to do another change of variable just because the change of variable makes this simpler. There is a variable that is actually famous that is called Landau variable, which is the following. This is a way to actually rationalize the square root here. Actually, the square root becomes even linear, the square root that you would get by solving this equation in p squared. And if you do that, then the integral becomes really super simple. So you get m squared minus epsilon, and then 1 over epsilon plus 2, and then plus 1 plus x divided 1 minus x, logarithm of x in this new variable x, plus higher orders in epsilon. Okay? And now we see the structure that we were discussing at the very beginning. I've computed the Feynman integral, right? What have I gotten out of it? Well, I've gotten some rational numbers. A rational function, well, it would have been algebraic in the original variables, but I've managed to actually rationalize it with this choice of coordinates here. Otherwise, it would be an algebraic function. And the transcendental function, which is a log, okay? And you see that these things are all mixed together, right? So there is a order 1 over epsilon. There is just, if you want, a constant, a rational number. At order epsilon 0, there is a number which has, if you want, what we typically refer to as transcendental weight 0, because it has no transcendental function. And then there is like a rational function and some function which has transcendental weight 1, which is a logarithm. We're going to say maybe a little bit more what this means tomorrow, transcendental weight, or at least what we mean with this term, but it just means transcendental weight increases whenever we have a logarithmic integration. So this is transcendental weight 1, this is transcendental weight 0, and there is a rational function. And all these things are mixed together, okay? And so one of the things we started from was actually the question, can we somehow separate this from this? As this one seems much simpler than this, at least to me. I don't know about you, but here there is like all the analytic structure, if you want, the non-trivial analytic structure that comes from the loop integrations is the structure that generates these branch cuts, so these discontinuities, and this has to be in the transcendental functions here. Okay, and I would like to be able to separate it because this is what is actually interesting. The rest are poles, singularities, if you want poles in the kinematics, and these are simpler. I know exactly where they come from, and somehow, as we will see, they can be separated in a general way. I hope I managed to show this to you. But okay, looking at this example in particular, then you see at least a structure popping up that we wrote last time, right? Sum of rational functions and transcendental functions. That's what comes out of this. I think I stop here for today, and then tomorrow we try to continue and we try to see where the structure kind of comes from. Well, I will introduce a different way to compute Feynman integrals, and then we will also try to connect somehow, well, to do a little bit of a connection with geometry, or at least with the homology of surfaces on which these integrals are defined in order to explain where this function comes from and where this piece comes from and how to separate the two of them. Okay, that's the plan. Any questions? Yeah, I'm done. Sorry.